Black holes, they are just the rock stars of the cosmos, aren't they? They capture our imagination like pretty much nothing else. I mean, we see them all the time in science fiction, right? Especially in these huge, mind-bending movies like Interstellar, where they're this terrifying obstacle, but also, maybe, a gateway to something else. So, what are they really?
All right, so here's how we're going to tackle this. First, we'll start with that famous movie scene we just talked about. Then, we're going to jump back in time a bit to get our heads around the science that predicted all this. After that, we'll look at the actual anatomy of a black hole. And finally, we'll take the plunge and venture beyond the event horizon to see what secrets lie inside.
Okay, so let's start with Interstellar. You probably remember that climax, right? The main character, Cooper, he makes this ultimate sacrifice. He pilots his ship straight into Gargantua, this massive black hole. And what he finds inside is, well, it's just bizarre. It's this five-dimensional space, a tesseract, where he can actually communicate with the past. Wild stuff. So when you see a scene like that, you just have to wonder, right? Is any of that even possible? I mean, let's say you could survive the trip. What would you really see? And that's the big question that's going to drive our whole journey today as we try to separate the Hollywood fiction from the scientific fact. Well, to even begin to answer that, we've got to go back, way back, like 100 years. You know, long before we had any photos, long before we even had a name for them. Black holes were, well, they were born on paper. They were this really strange consequence of Albert Einstein's groundbreaking theory of relativity. So the first part of his theory, this was back in 1905, showed us something incredible about how speed affects time. The idea is, if you're in a spaceship just zipping along at an incredible speed, time would literally slow down for you compared to everyone back on Earth. Now, you wouldn't feel it, but when you came back, you'd find out you'd actually aged less. It's wild. But then, 10 years later, he publishes his general theory. And this is where things get really wild. He showed that it's not just speed that can warp time. Gravity does it too. The stronger the gravity, the slower time flows. And hey, this is exactly what happened in Interstellar, on that water planet, right? Where 1 hour for them was 7 years back home. So, here's the big takeaway. Time isn't this constant thing we all thought it was. It's relative. And Einstein gave us two ways you can, well, mess with it. You can either move incredibly fast, or you can get really close to something with an insane amount of gravity. And to help people wrap their heads around this, Einstein came up with this brilliant analogy. He said, imagine space and time are woven together into a single fabric, kind of like a stretched out trampoline. And heavy things, like stars and planets, they create these dips or curves in the fabric. And that curve, that's what we feel as the force of gravity. Okay, and this led to a totally revolutionary idea. If gravity is just a bend in space-time, then it shouldn't just pull on things with mass like us or a baseball. No, it should affect everything that travels through that space. And that includes energy. It even includes light itself. And this meant that, theoretically, you could have an object with gravity so powerful, so strong, that even light couldn't escape its pull. You know, this idea was so strange that even Einstein himself was a little skeptical that these things could actually exist in the real universe. It took decades for scientists to prove they were real. The name black hole didn't even get popular until the late 1960s. And think about this. It took over a full century from Einstein's prediction until we finally captured that first ever image proving they exist beyond any doubt. All right, so we've got the theory down, but what is a black hole, really? Like, what's its anatomy? The name itself is honestly a little misleading. It's not some empty hole in space. It's actually the complete opposite. It's an incredible amount of stuff, of matter, packed into an impossibly tiny area. Basically, they're the ghosts of giant stars. See, throughout its life, a really massive star is in this constant cosmic battle with itself. You've got the outward push from all the nuclear fusion happening inside, and then you've got the inward pull of its own massive gravity. But eventually, it runs out of fuel. That outward push just stops, and gravity wins. It wins in the most catastrophic way possible. The star collapses on itself, then explodes in this brilliant supernova. And what's left behind is its crushed, unbelievably dense core. But here's the thing. Not every star gets this dramatic ending. There's a specific tipping point, a line in the sand, that was calculated by the physicist Subramanian Chandrasekhar. A star's core has to be at least 1.4 times the mass of our own sun for gravity to win that final battle. Anything less, and it just becomes a different kind of dense, stable star. But anything more, and that collapse is unstoppable. That's when a black hole is born. Oh, and by the way, our own sun, it's way too small to ever meet this fate, so no worries there. And it turns out black holes come in a few different flavors, you could say. The most common ones are called stellar black holes. Those are the ones born from single massive stars. But then you have the supermassive ones, and these are absolute monsters with a mass of millions of suns. We now think they're like the anchors at the heart of pretty much every galaxy, including our own. And scientists even have theories about tiny little primordial black holes, ones that might have been formed right at the dawn of time. So, okay, if black holes are supposed to be black, then what's that bright, glowing ring we always see in the pictures and in the movies? Well, that's called the accretion disk. It's basically a swirling vortex of gas and dust that's gotten trapped by the black hole's gravity. And as all that stuff spirals inward, it starts moving at nearly the speed of light. All that motion creates an insane amount of friction, heating it up to millions of degrees until it just glows fiercely with high-energy radiation, like X-rays. And this disk is what explains that strange, lopsided look we see in the famous photograph. So why is one side brighter? It's because that part of the disk is spinning towards us. Simple as that. And why does it look like a halo wrapping around the top and bottom? Well, that's because the black hole's immense gravity is literally bending the light from the part of the disk that's behind it, and it's stretching that light all the way up and over. It's just incredible. Okay, so we've seen the fiery outside. Now it's time to take the final plunge. Let's imagine a journey inward, crossing the boundaries that truly define what a black hole is. As we get closer, we'd pass through this totally surreal region called the photon sphere. Here, gravity is so perfectly, finely tuned that it can actually trap particles of light, photons, and force them into a stable orbit. Just try to imagine this for a second. If you could somehow stand there, the light from the back of your head would circle the entire black hole and come right back into your eyes. You could literally see the back of your own head. It's a mind-bending idea.
And then you reach it. The event horizon. This isn't some physical wall you'd bump into. It's a threshold, a boundary in space-time itself. It's the precise point where the gravitational pull becomes so powerful that to escape, you'd have to go faster than the speed of light. And since nothing can do that, once you cross this line, there is absolutely no going back. All paths, from here on out, only lead inward.
So where do all those paths lead? Well, according to Einstein's theory, they all end up at one place, the singularity. This is a single, one-dimensional point at the very center where all the mass of that dead star has been crushed into a region of infinite density. At this point, the curvature of space-time becomes infinite, and all the laws of physics that we know and understand, they just break. And this is where science pretty much ends, and pure speculation begins. We know gravity controls the flow of time, and we think gravity becomes infinite at the singularity. So what does that do to time itself? If you were to reach that center point, does time just stop? Or, and this is a wild thought, does the entire future history of the whole universe flash before your eyes in one single instant? The honest answer is we just don't know. But hey, before we get completely lost in infinity, let's pull back and end with a really crucial takeaway. It's a common myth that black holes are like cosmic vacuum cleaners, just sucking up everything in the universe. They're not. They're actually a stable, fundamental part of our cosmic architecture. You know, if our sun were suddenly replaced by a black hole with the exact same mass, Earth would just keep on orbiting it like nothing even happened. So here's the bottom line. As long as you maintain a safe, let's call it a social distance, you can orbit one forever.